We are going to continue with linear programming today for the second part. We're going to do the linear programming from the real world examples and take all the information from word problems. We're going to do one whole problem on the front side here, and we're going to go ahead and give it to you in parts as we get comfortable doing it, and then we will do other ones on the back where it is not giving you the information separately. So it says the Supreme Shipping Company can load its trucks with both rectangular and cylindrical containers. A rectangular container has a volume of 100 cubic feet and weighs 200 pounds. A cylindrical container has a volume of 200 cubic feet and weighs 100 pounds. Let X denote the number of rectangular crates carried by a truck, and let Y denote the number of cylindrical containers. They've done a really important part for you there. They have defined your variables. They've told you X is going to be the rectangular crates and Y is going to be the cylindrical containers. That's something you're going to want to do first when you're doing linear programming. It helps keep all of the information organized for your constraints, for your objective function, for your answer. So you want to do that first. Now, this is a shipping company that wants to ship as many boxes as possible. So what is holding them back from shipping those boxes is where we are going to get our constraints from. What constraint must be satisfied if each truck has room for at most 4,200 cubic feet of containers? The truck can only hold so much. In this case, 4,200 cubic feet. So we need to set up an inequality that shows that 4,200 is the maximum we can put in there. It says here our rectangular crates take 100 cubic feet. So 100 times each rectangular. The cylindrical ones are also going to take space, so I'm going to add here. And those take 200 cubic feet, so we're going to do 200 times each cylindrical one. And 4,200 is the total the truck takes. Now you need to think about what is happening right here. Which inequality is going to be needed. When we look at this here, this side is what the truck is holding of boxes. This is what the truck can hold. We want this to be the biggest possible because that's all that it will hold. So that needs to be on the open side of the inequality. This is the most that can go in there. Now we can fill the truck to the rim, so we also need that equal sign. All right, for our next one says, what constraint must be satisfied if each truck can carry a maximum of 4,800 pounds? If you've been on the highway, you've seen those weighing stations, it's important that you keep the correct weight on the truck. So 4,800 is the max this truck can hold. It says our rectangular ones weigh 200 pounds. So 200 times each rectangular. Our cylindrical weigh 100, so that's 100 times each cylindrical. And our total is 4,800 that the truck can hold. Again, this is what we want to be larger because that's the most it can hold. So we're going to have that on the open side of the inequality. And then again, we can fill it to the rim so it can be an equal sign. Now, since these are real world objects, there's no way you can have negative objects. So we also have to make constraints to show that. So X, our rectangular ones, have to be bigger than 0. They can be equal to 0, but they can't go into the negative. Same thing with our cylindrical. We cannot have any negative cylindrical containers. That just doesn't make any sense. So there's the list of our constraints. Those are the system of inequalities that we saw last time that we were graphing. So now we're going to want to graph these. There's a couple different ways that we looked at graphing. You graph with intercepts. So if we're looking for the x-intercept here, we plug in 0 for y, so this goes away. 4,200 divided by 100 is 42. So our x-intercept is at 42. I can plug in 0 for my x to get my y-intercept, and 4,200 divided by 200 is 21. And that is enough points to get a line. Once you have 2, then you want to graph through those points. There is an equal sign on these. So you want a solid line. The other option, of course, is to solve for y. So we can go ahead and subtract that 100x to get it to the other side, and we get 200y is less than or equal to negative 100x plus 4200. And then we divide both sides by 200, and we get negative 1/2 x plus 21. There's that y-intercept. We already knew that. It's right there. And then our slope of negative 1/2. Notice it goes down 1 and to the right 2, down 1 to the right 2. So either way you do it, you're going to be able to get the same line. Now with this one, the y is on the closed side of this. So y is smaller than this. We know that our y gets smaller as it goes down. So currently we've got this triangle right here. We don't try and shade until the end dark, because if not, you might get a big old mess on your paper. Now these two are technically already graphed for me because we said these were positive numbers and these were the positive numbers. And since we're only using the first quadrant, we've already eliminated the negative values. For our next one again, we can solve for y by subtracting the 200x. And dividing by 100. Oh, 48, sorry. And then we can graph that using the slope-intercept form. So 48 would be my y-intercept. My slope is this part in front of the x, negative 2, so I go down 2 and to the right 1, down 2 to the right 1. I can do that because my scales are exactly the same, so you always want to be careful with that. If you change the scale, you can no longer use the slope just like that. You got to think about the units. All right, we get a solid line again since there is an equal sign. And the y is on the closed side of that again. So we are below it. So the part that is going to be the quadruple shaded area is this part right here. This is where all of our solutions are found. We learned last time that's called the feasible region. So all of our solutions are found right here in our feasible region. That's all of our solutions. Now, the only places that you can maximize or minimize is at the corner points, these vertices. That's where you maximize or minimize. All of these are solutions, but you can only maximize or minimize at the vertices. Now, this one right here would be 0, 0. If we do that one, we're not really shipping anything. We've got no company, so that's definitely not going to be our maximum. But these right here would be our maximum, so those are the ones we're going to focus on. A, they told us to list out here. B is going to be this one, and this one is going to be C. So my A vertex is an easier one because we used that one to graph. That was at 24, 0. My B vertex also used that one to graph. That was my y-intercept, so 0, 21. The C is the one that you have to put more thought to it. If you've done a really good job graphing and it is a whole number, it goes right through the point here. So we can see it is 18, 12. If you have not graphed it to the T like that, you're a little bit off. You can always use a different method to find that. You can, it is the intersection of these two lines, so you can use elimination with both of these to find that point. You can use a matrix with both of these to find that point. You can use substitution when this is like this. You can put it in the calculator and find the intersection. So we have taught you several different ways of solving those systems. You can use whichever one you feel the most comfortable with. All right, so the purpose of our problem here, it says, suppose that Supreme Shipping charges $50 to ship a rectangular and $60 to ship a cylindrical container and wishes to maximize its income. There's the goal of the whole problem, and usually of the real world situation. People want to maximize their profits. That's what our objective function is going to represent. And it is a function, so it's going to be an equal sign, equation. And the profit that's going to be made is $50 times each rectangular plus $60 times each cylindrical. So there's our objective function. Again, that comes from the purpose of the problem, and the purpose is to maximize its income. Now, each one of these ordered pairs are x comma y, x comma y. So that's what we're going to use in here to find which one's going to give us the most profit. So we take 50 times 24 plus 60 times 0. And for A, that's going to give us $1,200. For B, we do the same thing. We just put in our second point here, 0 and 21. So that's 50 times 0 plus 60 times 21. And that gives us $1,260. And then for C, we are going to do 50 times 18 plus 60 times 12. This part is not hard math. It's just a little tedious because you're doing it over and over again. All right, as the manager or owner of this company, you're looking at this. This makes us $1,200. This makes us $1,260. This makes us $1,620. So this is the one we would want to do because that's where we maximize our profit. So for our answer, it should be a complete sentence, and we say Supreme Shipping should ship 18 rectangular and 12 cylindrical to maximize profits. Some questions are going to ask what should be shipped. Some are going to ask what is the maximum income. So that they gave us a combination here. The first part says what combination of containers should Supreme Shipping use to maximize its income? That's what we answered here. We answered the vertex piece, the one that tells us how many should be shipped. If they asked us what would be the maximum income, then the 1620 is the answer. So you want to be careful and make sure you're reading the question correctly. So 1,620 would be their maximum profit. All right, so now we're going to try one that does not have all the prompts because that's really what you're going to see in a quiz or a test question. And I want to make sure that you can pull out all the information that you need. Here it tells us each quart of the regular skin lotion that Harold makes contains 2 cups of oil and 1 cup of cocoa butter. Each quart of his extra rich lotion contains 1 cup of oil and 2 cups of cocoa butter. Harold makes $10 profit on each quart of regular lotion and an $8 profit on each quart of the extra rich lotion. If he has 12 cups of oil and 8 cups of cocoa butter on hand, how many quarts of each type of lotion should he make to maximize his profits? And what would his profit be? There's a lot of information here, and that's necessary in order for you to write all of the constraints, the objective function, and be able to graph this and answer the questions. So our first step should be defining our variables. That helps us keep everything very organized. That comes from right here. How many quarts of each type of lotion? That is on our unknown. So we are going to make X our regular lotion and Y our extra rich. Seems unnecessary to find those, but it actually keeps all of your information very organized, and it helps you write those inequalities with those variables, because everything from this point forward has to deal with the 2 variables we defined. The next part that you can do is the objective function, and that comes from the purpose of the whole problem. Here the problem is maximize your profits. So he makes $10 on the regular and $8 on the extra rich. So that would be 10 times each regular plus 8 times each extra rich. Now, what is keeping Harold from making tons of these and selling them to everyone and becoming a billionaire? Well, there's things that are keeping him from doing that. The fact that he only has 12 cups of oil and 8 cups of cocoa butter, that keeps him held back. That's where our constraints come from. So we're going to have one for our cups of oil, and we're going to have another one for our cocoa butter. So 12 cups of oil, this will be our oil constraint, and then this will be our cocoa butter constraint. So for the oil, the regular lotion says it takes 2 cups of oil. So 2 times our regular lotion. Our extra rich lotion says it takes 1 cup of oil. So 1 times each extra rich. Now we need to have an inequality here. Which one do we want to be bigger? Well, we only have the 12 cups. So that needs to be on the open side. We can use all 12 cups so we can have an equal sign. Now for our cocoa butter. It says it takes 1 cup for the regular, so that's going to be 1 times x, and it takes 2 for the cocoa butter, so that would be 2 times y. Again, this is all that we have, so that has to be the most, so it's got to be on the open side of that inequality, and we can use all of it. Now we need our other 2 that show that we're only using our positive values because we cannot have negative lotions. Now that we have our constraints, it's time to graph them. Again, you can graph them using intercepts. You can graph them by solving for y. So here I'll solve for y. I'll subtract that 2x to get it to the other side. And that gives us y is less than or equal to negative 2x plus 12. So here is my 12 for my y-intercept, and I'm going down 2 and over 1 for my slope. All right, for our next one, we subtract the x. And then we divide by 2. So our y-intercept on this one is 4. So I'm going to start there, and I'm going to use my slope of negative 1/2 to go down 1 and to the right 2. Forgot to discuss the shading on that first one. It is on the closed side of y, so it's going to be below it. This one is also on the closed side, so it will be on the close below it as well. So here we've got this part right here is the quadruple shaded. Again, the other 2 constraints, these 2 just say positive numbers, and since I'm only using the first quadrant, I've taken care of those 2. All right, now we've got to get our vertices. 2 of these are really easy. We've got this one here and this one here that we used for graphing. So we've got one at 6, 0. We've got one at 0, 4. Of course, we've got 0, 0. And then we need this one. It doesn't seem to be on a whole number, so I'm not going to try and use my graph for that one. We'll go ahead and use our calculator for that one. So I'm going to put in my negative 2x plus 12 and negative 1/2 x plus 4. Remember, you could also use a matrix here. You can use elimination to find that point. So there are other options if you don't want to use your calculator. Oh, I've got a weird window. So here is our 2 graphs. And the point we're looking for is that intersection point right there. So we hit second, trace, intersect. Enter, enter, enter. And there it is at 5.3 and 1.3. Now that we have all of our vertices, we are ready to plug them into the objective function. 0 going into both of those is 0, so that's an easy one. When I plug in the 6 here, that's 10 times 6, which is 60. When I plug in this one, that's 4 times 8, which is 32. And when I plug this one in, a little bit more thought, 10 times 5.3 plus 8 times 1.3, that gives us 63.4. Now this one is the max. That's the most money we make right there at 5.3 and 1.3. However, you want to think about this. That is unreasonable. Harold can't really sell a third of a bottle of lotion. You don't go to the store and buy a third of a bottle of lotion. So that is unreasonable. We would not want to answer that. Now 5.1 is in our solution set right here. So we could round this down because he could make 5 and 1. However, I'd like to show you that if you do round down to 5 and 1, that is $58. That is no longer the max. This is the max now, because you can only maximize at the vertices. Remember, we talked about that. Our maximum only occurs at the vertices. So when you round this down, you are no longer on one of those vertices, so that's no longer the max. So the answer we would really want to give here is 6, 0. 6 of the regular and 0 of the extra rich. That's going to get them the most money at $60.